Both Vishal and I are really proud to be here at Singapore and presenting you this talk. So let me go through the motivation of this talk first. So while developing software together, we found out that a lot of temporary files were getting generated on our system. So the problem that we had was a lot of temporary files were being generated on our file system. These temporary files had the same data, and because of these files a lot of disk space was getting utilized. So the typical or obvious solution to this problem would be writing a shell script which would go ahead and delete these temporary files, or you manually scout for these files and delete them. But since we had some experience with file system development, we thought the solution could lie in the file system itself, and that is how we came up with a prototyping of a storage efficient file system written with Python fuse bindings. So let's go and understand what are file systems first. So if you understand the problem that we had, a lot of temporary files were being generated and these files had to be managed. So who does that? Is the file system first. File system provides a way to organize, retrieve, store and manage files. So file system can be looked at as a hierarchical system wherein a file system would contain directories and files. Files are further subdivided into data blocks. File system is nothing but an abstract layer over your existing hardware where the files actually sit. So a file system is nothing but it maps name to objects. So if I say I have a file abc.txt, it's a name mapping to an object called file, and objects are being mapped to file contents. So abc.txt file contents would map to object abc file. File system are basically divided into two types. One is the real file system and the virtual file system. Examples of real file system would be FAT, ext2 and NFS, CIFS, those kind of examples, and the special purpose file system like procfs. So if you on your Linux box, if you do a cd/proc and if you do ls, it will list you all the processes. So it's kind of you're looking at a file system of processes. That is the power of capability of a file system. And the typical services that file system would provide for these operations like reading, saving and storing files are open, read, write and close. So if you have a look at the diagram on the extreme right there, the point we would like to emphasize there is the user applications are written in the user space, and the calls that are made from the user space get redirected to the file system, which actually lies under the kernel space. So let me ask you a question here. How many file systems are existing on your Linux box or your Mac box currently? Do you have any idea?
Supported?
Yeah, or how many are currently existing on your MacBook?
200.
Yeah, at least 2 to 3 file systems exist on your file system. But how are these being managed? Well, the answer to this question is in terms of VFS. VFS is a virtual file system. It's a manager for all file systems that you have existing on your box, Linux box. So it provides an abstract layer in the kernel space again, and every file system that you have in your Linux box is mapped to this virtual file system VFS with the help of mount point. Now what happens typically is when you try to query a file pertaining to a certain file system, the virtual file system gets the call, and based on the mount point of where the file exists, a particular file system is activated and the call is served. Let me explain that with a flowchart here. Let's say a user writes an application myapp.py and makes an open call. This gets routed to the glibc of the user space, as you might be aware. glibc open will create a system call that goes under the kernel space. Here is where VFS gets this call, and it calls its own VFS_open call to cater to the call being made by application and redirect it to the actual file system where it is supposed to reside. So for example, I create an open on a file which is pertaining to ext2 file system. So all the way from user to VFS, the flow remains same, but VFS is the guy who takes the decision of where this call should be routed to. So coming back to the problem that we had, So all these temporary files that were getting generated, we thought, why not there be a solution in the file system itself and write our own file system so that these problems do not occur or arise in the first place itself. Writing a file system itself on the flowchart that we had seen on VFS and in the file system would mean development in the kernel space. So but kernel space development is not so easy. The reason being, you need to understand the kernel libraries. You should know, you have the knowledge of managing disk and IO related information. Moreover, you lose a pointer and that's it, your kernel panics. So getting up the system ready and doing all the cleanup again takes a lot of time. Moreover, testing a module developed in kernel would require higher testing efforts, and again you are trying to bloat the kernel when you write something. As itself kernel is heavy and then you are trying to bloat it again. Issues like security may pop up, and again if you write something in the kernel itself, then you are asking users forcibly to use it. That's what you typically don't want. The flexibility gets lost out there. So as an alternative, let's look at the user space, if it could provide the solution there. So development in user space is advantageous because it has shorter development cycles. You have a lot of debugging and development tools to write application in the user space. Moreover, it's easy to update, fix, test and distribute. You are still maintaining the flexibility that user may want to use or not to use your application. And think, if you are developing your file system in the user space, it's like a wonderful place to be. You have a lot of control. You can do anything with that file system. And that is what we aimed at doing. Let's understand how we went ahead about doing it with Vishal.
So the mechanism to develop file system in user space, it is called Fuse. Fuse is an acronym for file system in user space. The best thing about Fuse is that you don't have to write any kernel code, and it's a loadable kernel module. So you just need to install Fuse on your system and that's it. You can start writing your own file systems. And another thing is, Fuse is for all the users. It allows any regular user who doesn't have root privileges to write a secure and a file system that can be mounted by him or her. So the benefit is that even without the root privileges, you can write your file system, you can mount it, you can get it shared with other people also. So user operates on a mounted instance of his or her file system, and the behavior of this file system is exactly same as a native file system. So all the Unix utilities like cat, touch, anything you name, and any application that has been written with the POSIX libraries using calls like open, close, create, read, write, they will work exactly in the same way. So there is absolutely no difference between the behavior of a file system that has been written with Fuse or on a native file system. And important thing is, as Chetan had told in his slides, that you have real file system and virtual file systems. So you wouldn't really want to write something on the disk with the help of Fuse. For that you have your native file systems, but rather you would want to become more creative and write some virtual file systems. So Fuse allows you to creatively assume anything as a file. So you can say you can do file operations on a remote directory. So there are Fuse based file systems like SSHFS are there who can allow you to do that, and you can do operations on local disk, on a network device, and you can abstract anything as a file system, maybe even a database. So let's see how Fuse accomplishes these things in detail. So let's dive deeper. So as Chetan had told, how application file IO flows till VFS open. So say the green box is the file system that you have written. So this file system exists in the user space. The boundary separates both the spaces. So our objective is to serve the request of myfile.py, the open request from this application, from the open implementation of the custom file system. So you have to mount your file system. Once you mount it, these three components start functioning. So the first component is called fuse.ko. That is the loadable kernel module and is registered with the VFS. So any request which comes for custom file system is routed to fuse.ko. Fuse.ko creates a special device called /dev/fuse. So this device is accessible from kernel space and user space. Now VFS directs the request to fuse.ko. Fuse.ko writes the request on the fuse device, and from the user space the custom file system is linked with a library called libfuse.so. Libfuse.so polls the fuse device and reads the request. Once it has read the request, it will send the request to open. Open will handle the request and send the response in the same way. So that is exactly how a file IO happens in Fuse. So as you see, for every file IO request, we hop from user to kernel space 4 times. Now that we know how Fuse functions, for a developer, what are the things that it offers? So Fuse allows you to develop your file system in many languages: C, C++, Java, and of course Python. And since we know that fuse.ko is a kernel component, so you need to have some kind of wrappers to interface with this. So if you want to implement your file system in Fuse in Python, you have to use a binding called Fuse Python. This is the same binding we have also used to develop our own file system. Fuse is an open source project, and to install it on Ubuntu is a very easy task. Just need to install the Python Fuse package. Once you do that, you just create a mount point, write your file system, run it on your mount point. That's all. Your file system is up and running. Any application can actually access the services of your file system now. Once you are done, you have to unmount your file system with the help of a utility called fusermount. So as you see, that mount and unmount are being done by any normal user and in the user space itself. So to develop any file system in Fuse, you need to know the Fuse APIs. So your application will inherit a class in Python. Your application will inherit a class, and they have to implement these APIs. So Fuse APIs allow you to write a full-fledged file system, which allows you to perform file management, directory management, or metadata operations on your files. As you see that the calls are very looks like very standard calls. The signatures of these calls are also standard and very similar to POSIX. Now that we know about internals of Fuse and how Fuse APIs look like, let us see how exactly we solved our problem, the ones we had discussed in the beginning with our own file system. And let me call upon Chetan for that.
So just to reiterate the problems we had, a lot of temporary files were being generated with the same content, because of which disk space utilization was going high. So we solved this problem with a prototype file system called as SEFS. SEFS we named as Storage Efficient File System. The efficiency came here in the form of data deduplication and in the form of compression. So for the benefit of people who may not know what is deduplication, deduplication is nothing but, let's say I have 5 temporary files and all having same content. Why do I store these files independently? Just save one file and keep the references of these in multiple places, and whenever I call the reference, I just use it to use the same file to give the data with which it had. So as Vishal had explained, you can abstract anything as a file with Fuse. So here our SQLite database is being abstracted as a file system. So the database is a file system, and each row in a table would designate it as a file. So as we know, file system is a group of files. So database here acts as file system and row in a table acts as a file. SEFS was developed in Ubuntu 11.04 with the Python fuse bindings, as Vishal discussed, and it provides all the typical services that a file system would provide in terms of open, read, write, call, and everything. Let's see what's the architectural view of SEFS. So here the green box, myfuse.py, is the actual file system that we developed. So when a user application makes a call or performs some file system operation onto the fuse, myfuse.py, myfuse.py interacts with the database over here. So the interaction happens is through a database interface, which is this red box, SQLite database interface, which actually interacts with the PyLibrary project that we have developed. PyLibrary is an open source project which has different varieties libraries for handling database operation, to provide deduplication with crypto.py and compression related functions in compression.py. So all these together help us in effectively achieving storage efficiency with data replication and compression. But where is this efficiency coming in? So this efficiency lies in the database architecture. So let's look at the database schema here. So typically what happens in a file system? File system is nothing but files, file metadata information, and the file contents. So that is how, that's on a simple philosophy of that, we have kept our database schema as well. So we have two tables, metadata that contains the metadata information of file like ctime, atime, inode information, and the data table which actually contains the file contents. So let's see things in action here. So let's say I create a file hello here first and add content to it. So two tables get updated. One is the metadata table, which lists the file with access time, atime, and inode related information, and the data table which gets all the contents of the file. But let's say I create another file hello underscore again here. What happens? So the metadata table gets updated with another record for hello underscore again, but before writing the entry in data table, it checks the SHA value of that particular file contents. It sees that hello contents and hello underscore again contents are same, and that's why it avoids updating the data table, and in effect it just writes a reference to it. So here the actual record, the data record is hello world, which is record 2, but the references are kept here for hello and hello underscore again, so that you can see with these arrows. So this is where we are doing the actual data deduplication. So in effect we are storing the file contents only once, but just we are maintaining the references. Moreover, the problem of high disk space utilization was solved with the compressed data. So we have a column here called compressed. So this would maintain the compressed information of the actual file contents. So yeah.
Quick question.
Yeah.
Why is length stored twice, once in metadata and once in data?
So in order to perform operations like ls and all, so we were banking on metadata table. To, let's say if you do ls on the files, all the files, it has to list hello PyCon, hello underscore again. It should list the inode information, it should list all the metadata related information. So that's why length was kept twice there. So we need not have to call two tables at a time. In one query itself we could get that.
Okay.
Yeah.
So what happens when two files have different content but the same hash? You cannot say this is the same content, but they won't do the same.
So yeah, so the SHA1 value that we are using here, the possibility of getting to the event where it happens is very high. Yeah,
Highly unlikely.
highly unlikely.
It's possible because
SHA is extremely
Unlikely,
hard,
yeah.
mathematically speaking.
I know, but you can tweak it until you get the duplicate of that.
Well, good luck.
That's you're trying to find some, like if someone's doing a DOS against something, if you want to start submitting a lot of things with the same hashes, we already know what's already in the table.
Yeah.
So if somebody's intentionally trying to find something,
Yeah.
Intentionally,
it's an,
it's-
an
Yes.
intentional attack.
Okay.
Okay, I understand.
I will not call attack, but it's just intentional. You can get a same hash,
Yeah.
just trying.
Yeah.
So how do you detect those collisions?
Maybe add another layer of detection there. So wrap SHA1 value with SHA256 or maybe. Yeah, but again, that likelihood of occurrence would be the key. And
Maybe one
Set,
suggestion
yeah.
could be
Okay.
not only checking the hash,
Mhm.
but also the size. That will
Okay.
avoid more
Mhm.
collisions.
okay, yeah, that can be done.
Checking for the hash.
Uh,
I'm consuming if I'm doing really a lot of files checking.
sorry, didn't get that.
Is the hash function efficient? How long does it take to compute the hash?
Okay, yeah, it's pretty, like, we haven't done any performance measurement on that. So, but is the PyLibrary project that we are using for this, which is again homegrown. So it typically involves milliseconds of time to calculate a hash.
And again, it depends on the content of the size. So if you have a very big files, then of course it would be slower.
Yeah.
So again, that's a price we have to pay to achieve efficiency in the storage.
So
This only does whole file dedupe, not block dedupe. Is that correct?
no, this is file-based deduplication. So it's a more of a prototype implementation that we have come up with. So based on this, we have now ideas to do further deduplication. So now in this case, if you ask me a question, I update hello, what happens? Then again, if I query hello, I'll just get to the updated file, but hello underscore again will also point to the updated content. So error conditions like these have not been handled here, but we are aware of them, and the work is going on to complete these. So now that we understand how efficiency is built in SEFS, let's look at the Fuse APIs that we have developed with Vishal.
So in order to write your own file system, you have to use Fuse bindings. So our Python based file system implementation uses Fuse Python bindings, and the API and as I have told that any Linux utility will work in the same way as any standard file system on our customized file system. So if you say you create a file, remove it or append a file, this is a sequence of operation that follows in Fuse APIs. So if you want to create a file called ABC, so first thing that is called is the getting the attributes of the file. After getting it, we would like to create it. And to create, we see if we can open this file. If open fails, we can say that this file doesn't exist, and we'll end up creating the file. And there are things to know, like in Fuse there is no close call, so you cannot close a file, you have to release it. And for any operation, getAttr is always called. So if you want to write your own file system, getAttr is a must. It is a mandatory implementation. Without it, you cannot have a functional file system. So getAttr is like when you do a ls, so you get the metadata of all the files. So for each of those files, you call get attributes for each file. As Chetan had described in his architecture, that all the operations are actually built around the SEFS database we have. So let's look at the code. So this is how you write a very basic file system like SEFS. So you have to import Fuse bindings. Then you have to tell the version of Fuse bindings, that is 0.2. This is the actual file system, and it is actually inheriting the Fuse class, and this class will implement all the APIs of Fuse class. In the constructor of this class, you have to set few things, like if you have a file system, you have to have a root. So we created a root. Now the interesting thing is this. See, we are abstracting a database as a file system. So the root creation is actually, see what I am doing here is I am creating an object of the database, Once I have done that, I try to open this file called slash. So the behavior of this call is, if this file doesn't exist, it will create that file. So actually I am creating root in my database. Then I just write some data into it, that it's the root of our file system, and then I set metadata details of this file. So I set the times, which is the current time. So I set 3 times, like m time, a time, and c time of this file, and update them in the database, and that's all, I'm done. So that is how I initialize. You can initialize your file system with Fuse. So these are very basic things that you have to do. Now let's look at the get attribute function. So this was what I was talking about. So this is a must implementation for any Fuse based file system. Here again, see, everything is done into the database. So we create a object of the SCFS database, and we create a structure called stat. So stat is a structure which keeps information about the file metadata. It's a standard structure and it's exposed by Fuse. So you have to fill in the details in this structure. So details should be like this. You get the context. So context call will get you the GID and UID, the user who has mounted the file system. Then you check if the path that has been passed to the getter, if it is a root. Then if it is root, then you just set that the mode of this file is, it's a directory, and the permission that you want to set. Otherwise it's a regular file. You set the nlink is the number of soft link this file has. So to root you have 2, because the parent and the current directory, you have 2 links. For any regular file you have only 1 link. You set the UID GID with the context information. Then see, again we are doing a search in the database. We see if this path exists in the database or not. If it exists, we just get all the U times from the database. We read them, we fill in all the information. If it doesn't exist, we say that the file doesn't exist. So the beauty of Fuse is, see, we are abstracting all the database operations like as if they are behaving as a file system. And this is just beginning. You can do anything here. So in fact we are just exporting all the database row here as a file. When you do a ls, you are actually listing rows of your database. That's the same way you have calls, like you want to create a file. Again we just try to open this file. If the file open fails, we will create this file in the database. We set the times. I have created an object of the database in the beginning. So with that database, I'll just update the times in the database, and I just return. That's all. How you write a file? You get the information like path of the file, that would be the name, the data, and the offset at which you want to write the file. See, again, you can choose to implement how you implement this function. So like here, see, I get the length of the data, create the database object, and just write this data into the database. That's all. I haven't handled at what offset I'm writing it. So it's like every time I start at the offset 0. So the fun with Fuse is you can experiment and you can choose what to implement and what not to implement. So if you don't want to export few things like in SCFS, so far we haven't handled any directory operations. We don't have to implement them. So even if you don't implement them, your file system is functional. It will work. There is absolutely no requirement to implement everything other than the getter.
So this file system that you just, given what you just said, the file system you implemented is a single directory with files.
Yeah, it's a flat file system.
Flat,
Yes. Then after writing this prototype, we have some learnings. So one thing is that you should know what you want to achieve first before start developing. So like we had a long discussions not on the how to do it, rather more on what to do. So we wanted to implement storage efficiency, and who should implement it? Then we finally decided that it should be done in the database itself. And what functionalities to develop now and what we can postpone, that decisions we took in the beginning of the development itself. And important thing is you should know how Fuse APIs flows. So for each operation, what is the flow of API, you should know to implement a right behavior.
That was the toughest part while we were developing. So let's
And
say I need to write create, then what path it takes? We don't understand that.
so you need to know that you first call the get attr, then you call the create, then it called open, then again create, and you release it. So if you want to implement a functionality, you should know that this is the flow of APIs, and these APIs you have to implement to deliver that functionality.
How did you discover the flow?
By
Usually
instrumenting all the calls with printfs.
Yeah.
Trace is also
So if you actually look at the code that we have on your laptops, then you'll find with every statement you have associated 1 or 2 prints. That's how we come to know.
And the bad thing is that the documentation of Fuse API is severely limited. So it's more of how much you experiment. It's trial and error. That's what. And other important thing is the performance of such file systems. So as we had seen in the internals of Fuse, see, for each file IO that is coming from the application, it goes to the kernel, then it again flows back to the user space. And shall I go back to the slide? Just a second. See here. So the flow of one single operation is like from user space to kernel space, from kernel space here to again user space. You process the request, then again from user space to kernel space, then flows back to kernel to user space. So you are essentially doing 4 context switches, which is very, very expensive. So any file system which is based on Fuse should not be designed for efficiency, rather it should be designed for functionalities. And the benefit is that you can write your file system very quickly in a very short time and experiment with your thoughts. With this, I would like to request Chetan to conclude the talk.
So to conclude, looks like development of file system is not that difficult. You can do it very easily with Fuse bindings. And Python, you can do this with any other programming language, but Python provides you that leverage of doing it rapidly with Python Fuse bindings. SEFS has really been a thought-provoking or prototyping implementation that we have come up with. So with this, we now have a good idea of what we can do next and what level can we take this project to. And of course, development of file system with Fuse, there is no end to creativity. You can do much more things like these. The existing creative applications that you may find on the net or anything are like SSHFS, as Vishal discussed, or Wikipedia FS. All these do a good job with their file systems. And hope this presentation inspires you and you to write a file system of your own, and we find it on the internet soon. So here's some further read or kind of references that we used. We had a look at some of the existing file system, and these are some of the good ones that we found. And of course, Python Fuse bindings that we used is hosted on SourceForge. Here's the link. And reading contents on file system and VFS and all came through Linux internal manuals. So if you have some feedback to us, you can give it here. We would like to also hear some good comments and bad comment as well. Thanks.
All right. Thank you. Anyone else got a question?
Well, okay. So the SQLite guys actually had do some measurement, but it's already expected.
Okay.
For large files, it's not a good idea to say.
Correct. Yeah, that's why this for smaller files and a prototype implementation we chose a database thing. But of course, if you have 1 GB or TB of files that you can't do with database there, then we'll have to do it in the native file system way.
Well, you're talking about megabytes.
Okay.
Yeah. So No, just a comment.
Yeah, that we are aware of. Yes.
So when your application writes to your file system, you will need to somehow buffer that all the writes before you dispatch it to CFS. How are you doing that right now? Is it in memory, or are you writing to an actual temporary file on disk first?
No, it's a memory based. I think Vishal can take this.
So when you give it a write request, so how does the native write behaves?
Okay, so let's say
Even
okay. So let's say I'm the I'm the application developer, and I'm writing to a temporary file to your file system, and so let's say this temporary file is like 10 megabytes.
Okay.
So where do you store that 10 megabytes of content before you dispatch it to SEFS?
Okay. See, when you write on a file, you have to tell how many bytes you want to write. Right. So you can open a file and start write. You don't have to do in a single bunch. You can create small chunks. So like by default, if you don't give any buffer, Fuse itself it gives you 4 KB buffer. So you can write in chunks of 4 KB each time. If you want to write a bigger file, maybe you have to increase that buffer. But I don't think you need to do it explicitly. I mean, you can start reading in smaller chunks and keep on writing it in multiple write calls. Is that answer the question?
Not really.
Okay. You have to have the whole contents of the file on hand before you calculate the hash, though, right?
Okay.
In your case.
Okay. Yeah, it is. It is. So
you
for
accumulate the entire contents in memory. And
right.
calculate the hash.
Right now it is everything is in RAM.
So Fuse takes these character when you do write, then it takes byte by byte. But if you have to get the content of all together, then you'll have to do it. Right now we are doing it in RAM. But yeah, maybe for large files, you may have to look at other alternatives.
For your case, like if it's a 10 MB file, you can keep it in a buffer. So yeah, you can keep it in a buffer. Like we have something called C-string IO class that you can use. So you write your data into that buffer, keep on reading from that buffer and give it to your file system. You can keep on writing. But 10 MB at a time, I don't think even Fuse can handle. So you have to do it in chunks. So right now we haven't handled for such big files. Fortunately for us, these files are very small, so we didn't have to do that.
All right.
So right now, I've written a file system using Python Fuse.
Okay.
And when I put a 1 gigabyte file in, and I guess one of the issues with that I can't figure out with Python Fuse right now is how to block the writes while I'm calculating the checksums. I'm calculating the checksum at flush when I know that all the content is coming.
Yes.
And it takes a really long time because it has to scan everything from the start again. So I'm still trying to find a solution to that. I'm not calculating it on the fly because an application could potentially write to the, seek back to the front of the file and write to it, and then it will mess up the whole hash. So I'm still thinking.
Okay, I think we can discuss it later about the solutions.
All right. Thank you very much.